Okay, so this is the next question that we got on the menu today, a two-part question. Let's just address the first part on its own first, and then we can move on to the second part. So the first question is asking us, a car can decelerate at -5 meters per second squared without skidding. That just means like this is its maximum acceleration. Um, and this was tested on a level or a flat road. Now it's asking us what would be the magnitude of its deceleration if the road were inclined at 12 degrees, ignore the A accent circumflex, 12 degrees uphill. Assume that the static friction coefficient is the same, which is pretty important. Okay, so essentially what we have here is a situation like this. This is definitely not to scale because this angle is much larger than 12 degrees, but it's just to make the point clear. So this is 12 degrees, and we have our car, vroom vroom, like this. And under normal circumstances, we would have a deceleration of -5 meters per second. So this is A, and let's just call that the brakes because I would assume it's the brakes that are causing that deceleration. So let's call that AB for brakes is equal -0, not -0.5, -5.0. meters per second squared. But because we're going uphill, we know that gravity is also going to provide, to a certain degree, a little bit of deceleration that is also going to go down the hill. Now, gravity is accelerating straight down like this. So maybe I'll do that in red. This will be AG, which is equal to 9.81 meters per second squared. Okay, but you know, a lot of this acceleration is really just keeping going, is really just absorbed by the fact that the car is like being pushed into the ramp itself. So not all of this gravity is going to be incorporated into you know, the deceleration of the car as it's going uphill. So it would be instead better if we could break this down into a coordinate system. Oh geez, that's probably not a great place to draw that. I'll redraw that. AG is equal to 9.81 meters per second squared. Okay, so instead it would be better to break down the gravitational force into components. So this would be AG, if we define our coordinate axis like this, this can be our x direction, this can be our y direction. So this can be AGX, and this will be AGY. AGY. Now AGY is not going to be relevant to this angle. I mean, AGY is not going to be relevant to the overall deceleration as felt by the car itself, because the acceleration AGY is counteracted by the normal force. Yeah, so this could be a little bit confusing. Maybe I'll draw this in a purple color. So this is AN for normal, and that's going to be equal to AGY. So the only things of relevance here is going to be AB and AGX. Okay, now to determine what AGX is, we first need to keep in mind that this angle here is also 12 degrees. So it's also going to be theta, like that. Okay, so the overall acceleration, we're just looking for the x direction acceleration. So we want, according to this tilted axis. So the total acceleration is going to be equal to the acceleration of the brakes plus the acceleration of gravity, but just the x component of it, right? So we should rewrite this, AB, we already know that as a value, but AGX, we know that, you know, seeing how this right here, this area right here makes a right angle triangle, we can see that AGX is just going to be the, you know, knowing that this angle is 12 degrees, it's going to be the opposite. So that's going to be sine of the angle times 9.8. Because 9.81, that's the hypotenuse of this right angle triangle. Maybe if I draw this, that will be a little bit more clear. So we definitely have to be sine of that angle. So it's going to be sine of theta of regular AG. Now subbing in our numbers for this, AX, we shall get, well, we originally had our 5 meters per second. Let's keep the signs consistent. So we're going to have negative 5.00 meters per second squared. Assuming positive is going to be up the slope. And then we have to plus, but this is negative as well since it's going down the slope. So that plus is really kind of just like a formality thing. This is going to be sine 12 degrees multiplied by 9.81 meters per second squared. Okay, so running this through our calculator, we should find the result of this. So sine 12 degrees times 9.81 plus 5, and we have a total deceleration down the slope of 7.04 actually, rounding that to 3 sig figs, meters per second squared down the slope. Negative actually. So down the slope is really just like it's kind of redundant if we have our axes defined like this, but otherwise, yeah, so we would expect this would be the new deceleration, which makes sense because we'd expect a larger magnitude of deceleration if we're going uphill, because gravity is also decelerating us. That it would be great to show that as a calculation, but yeah, cool. So part 1 is set up good, but now we got to address part 2. Okay, so I'm gonna just write this out real fast. Part 1 would be to show the result of the calculation. Okay, now let's move on to part 2 of this question. Pretty fun. Pretty fun. Part 1 was fun. Hopefully part 2 is just as fun. Part 2 is asking us, a 6,480 kilogram helicopter accelerates upwards at 0.57 meters per second squared while lifting a very heavy 1,190 kilogram car. What is the lift force exerted by the air on the rotors, and what is the tension in the cable? Okay, so let's actually draw a diagram of what's going on here. So I'm not very good at drawing helicopters and stuff, so I'll just write heli up here. And what was the mass of the helicopter? So that's 6,480 kilograms. And it is attached by rope to a car. And that car is going to be 1,190 kilograms. Cool. And we know that this whole system has an upwards acceleration of 0.57 meters per second squared. Okay, so that's the total acceleration. And yeah, so the first part of the question, or the first part of the second question, is what is the lift force exerted by the air on the rotors? So the forces that we have here is we have the rotor force. So let's just call that FR. We have, let's call this FGH for the gravitational force from the helicopter. And then we have the gravitational force of the car, FGC. And we have a tension force in the cable, but that's more for part B, so we won't worry about that too much for now. So essentially, we're trying to solve for the rotor force, and we know the net acceleration. So we want to set it up this way. So the sum of all forces is equal to the total mass, let's call it mt for total, times the acceleration, which we know is, let's call that acceleration an for net acceleration. And we know that this is going to be the result of Fr, the rotor force, minus the FGH, the gravitational force of the helicopter, minus the gravitational force of the car. Okay, so given this, we want to isolate the rotor force. So to do that, well, we just send FGH and FGC to the other side. MT AN plus FGH plus FGC is equal to the rotor force. And to write these out in full, we know that MT is going to be M car plus the mass of the helicopter, MH, multiplied by AN plus mass of the helicopter times G plus the mass of the car multiplied by G, and that is equal to Fr. Okay, so subbing in our numbers, our car mass is going to be 1190 plus the helicopter, which is 6480, times the net acceleration upwards, which is 0.57, plus the helicopter times gravity. Actually, for these two, we can factor out the g, so it'll just be a little bit easier. So 9.81 is their acceleration, and then it's going to be 1190 plus 6480. Okay, and we can actually make this calculation even a little bit more easy. Just to type in our calculator, it could be like this. So 1190 plus 6480, and that is like we factor out that this term and this term, and then it's just going to be 0.57 plus 9.81. Okay, fairly straightforward. So let's send this in our calculator and figure out what that is. 1190 plus 6480 multiplied by 0.57 plus 9.81, and this force is going to be 79614.6 newtons. And to get this into significant figures, we were given two significant figures based on this. So 2SF, we have 8.0 times 10 to the 1, 2, 3, 4 to the 4 newtons. This is the rotor force of a helicopter. Okay, pretty cool. Pretty cool. Okay, so that was the first part of the question, is what is the lift force from the rotors? We got that calculation. The next thing that we need to consider is the tension in the cable. Assuming that the cable itself has no mass, which is not always true, almost never true, but we can assume that. To do this, we want to look at the car on its own. So here we have car. We know the car is going to be 1190 kilograms. And just looking at the car itself, we have a tension force and going upwards, and we have our gravitational force, FG car, going downwards. And we know that our net acceleration is also going to be that AN value of 0.57 kilograms. So to solve for the tension, we're pretty much going to follow the exact same procedure that we did here. So maybe I'll do this in a different color, like blue, if my software can be cool for a second, please. Okay, let's do this in blue. So we know that the sum of all forces, okay, I guess we're doing this in black. So the sum of all forces is equal to the mass of just the car itself. Just the car itself, right? Because in here, as we scroll up, we are just dealing with the car here. Mass of just the car itself multiplied by the net acceleration, because, well, they're physically attached to each other, so they have to have the same net acceleration. And that is going to be equal to the upwards force being positive, so that's going to be T minus FGC. Okay, and just like before, to isolate T, we have mass of the car times the acceleration upwards, the net acceleration, plus FGC, the gravitational force. And we know that this is, the gravitational force is a mass of the car multiplied by gravity, factoring out the mass, so we can get a calculation like this. Is equal to T, and let's sub in the numbers to figure out what that is. So the mass of the car, that is 1190 kilograms. AN 0.57 meters per second squared, plus gravity 9.81 meters per second squared. Okay, let's calculate that, and we can find the tension in the cable. So, so my results for this calculation has got to be 12.352 newtons, and also to two significant figures. We will get 1.2 times 10 to the 4 newtons. Okay, so there's a lot less tension in the cable compared to the amount of force that the rotors are supplying, but that makes perfect sense because the rotors are pretty much the ones that are allowing that tension force to exist in the first place, and the entire weight of the helicopter as well is dealt with that. So yeah, this makes a reasonable amount of sense. Everything is good. Okay, so we don't have that solution here, but yeah, if it was here, I would assume it'd be done the same way and all be good. Solution is missing. Video answer available. Cool.